Thank you, everyone. How's everyone doing? Uh, so today we'll follow from where we left not yesterday, last time. First with a quick review of what we covered to make sure that we are able to follow the concepts or clarify any questions that we may have, and then continue to the new material. So first, can anyone mention what some of the geohazards that we talked in the first lecture? Yes, Chris. Correct. Liquefaction is one. What's the most obvious one? Earthquakes, what do they do? And like, why do we care about earthquakes when they happen? Landslides, but liquefaction, ground shaking. Yes. So yes, that's usually like ground shaking that affects everything, and then that will trigger liquefaction, landslides, surface fault displacements, and so on, tsunamis, and so on. What are some of the types of different plate boundaries that we discussed last time? There were three of them. Subduction zones is one, and in what is the sense of motion in that? Like, do they play? Yes, they converge, and yes, one subducts under the other. And the other were like mid-oceanic ridges, which is like where you have formation of new crust as the two plates move away relative to each other. And then you have also transform zones, which is when one is sliding next to the other, and you have strike slip faults like in California. So this is when we look at the plate tectonics and movement of the crust on a macro scale. But if we were to look at it more locally, then what are the different types of faults that we discussed? Strike slips. And those are associated with which type of plate boundary? Correct? Reverse. And where would we expect to see reverse faults? Correct. And the last one? Normal faults. And that's typically in areas where you have extension. And then the different types of seismic waves that we saw. First of all, we group them into two main groups, body waves. Those are the seismic waves that travel through the bulk of the Earth crust. And then we have surface waves, which are the ones that are traveling along the surface. For body waves, the two most important ones are the P and S. Those are the primary and secondary waves, and we discussed the different sense of motion. One is extension and compression, the other is shear. And Rayleigh and Love waves, they have to do with Rayleigh waves is the combination of SV and P, so it has like a retrograde motion, and then Love waves is the SH waves, but then they decay along with depth. And we will see how all of this is important in today's lecture. Also, before we begin with the new material, I don't know, most likely no one of us felt it, but did you read on the news of like a 4.1 magnitude earthquake that happened in Canada, like close to Toronto, I think yesterday? No? Okay, so let's look at this and see how it's relevant to what we discussed. So this is the report that USGS has produced. And what's more interesting maybe for us is, so it's a small magnitude earthquake. We don't expect this to cause any damage. Yes, please, Saba. Thank you. Yeah, I keep forgetting. So where is it? Okay. So this is the USGS report for this earthquake. So this was, the hypocenter was north of Toronto. And maybe for us, what we can see, look weaker more is so we will talk about the modified Mercalli intensity values today, but also we can look at the PGA. So PGA is the peak ground acceleration from this earthquake. So it's a small event. It produced 0.05 G very close to the center. And as we see, and as we described with like the attenuation, as you go away, further away from the source of the event, the ground motion reduces. And we can also look, so this is the contour map that shows that. And because it's a small event where it can be thought as a point source, you can see that more or less we have concentric circles around it. But one thing that we can notice is the distance, let's say, between let's say this is 0.05, this is 1, and then 0.01 is here. So if this is 30 kilometers, it's more than 120, 150 kilometers, the distance that it took to attenuate from 0.01 to 0.001. So let's compare this with another earthquake of similar size. That happened in California. So the previous one was 4.1, this is 4.2. And we can see again at the PGA contours. So this is same scale. Look at 0.1 is here, 0.001 is here. So the same attenuation in terms of amplitude happen in 30 or 60 kilometers. And that has to do with what we talked about, the like size, how the attenuation in the crust of the Earth is affecting how strong the shaking is. So because the rock and the bedrock is much stronger around East Coast, because that hasn't experienced so much seismicity and it's not as fragmented, the seismic waves can travel a lot longer distances without being attenuated as compared to California. And that also tells us that the size of the earthquake alone is not enough to describe the importance of that event, because at the end we care about shaking, and that is not only controlled by the source and the magnitude, but also where the earthquake is located. Yes, please.
At a place farther than the epicenter, we can get a PGA higher than.
Yes. Can you guess why this may happen? Constructive. Correct. We will see how constructive interference is creating pulses in the seismic waves. But there, like if you remember, we talked about the source, the path, and the site. So it all, most commonly, you will see very larger ground motions inside basins. And that's because you can have seismic waves that are entering the basin, and because it's much softer, they are amplified, and they are not allowed to escape. And the Mexico City earthquake was a classic example of that, where it caused buildings to collapse inside the Mexico basin and very small ground motion on the edges. Yeah, but yeah, great question. maybe before we move, something else that we will look at today is, so what can we see about this earthquake? We can see the size of the earthquake. This is a 4.1 in this magnitude scale, which we will see it's the body wave magnitude scale, and the depth is 11.5 kilometers. So that happened 11.5 kilometers below the surface of the Earth. And for this one, where says California has a better seismic network, so they have a lot more information that they can collect. We also see the moment tensor. So this is one way that we can represent the earthquake, especially for small earthquakes. And this tells us, if you remember, we described for the to define the geometry of the rupture, the strike of the fault plane. So in these beach ball diagrams, these two planes define the two possible planes that can produce this earthquake. And we see here both of them are vertical, implying that this is a strike slip event. And the shaded region is maybe, let me see if I can do that. So we will revisit this in more detail, but one way that we can think of an earthquake, if this is a fault, and you have this sense of motion and then the confining stress, then essentially in a beach ball diagram that can be interpreted as like this moment couple and this moment couple to produce equilibrium. So there is this is the side, these two sides are the compression sides, and these are the extension sides. So these are the shaded regions in the beach ball diagram, and the other ones are the light ones, which is also shown here. So if we go back to the to the moment tensor solution for this earthquake, this is what this figure is telling us. Okay. So let's move to the new material. So why do we have earthquakes? We have earthquakes because we have the different plates moving relative to each other, and that is causing an elastic strain to accumulate along their interface. But the strength of the crust is not infinite. So when we reach the strength of the crust, then you have like slippage occur, which is what we feel as the earthquake. And so you can assume, like, starting with at rest conditions, you load the system, it reaches its failure point, it displaces, releases the earthquake, and then that cycle repeats again. And if we were to see that in terms of shear stress evolution, we start from some point in time, we see stress increasing, reaching the strength of the material, releasing, and then accumulating slowly again. And the difference between the stress before the earthquake and the stress after the earthquake is what we define as stress drop. And this has to do with essentially how compact is the energy that is released, because the larger the stress drop, the more amount of energy is released within a unit of volume. And the general theory that describes earthquakes and how they load and unload is the elastic rebound theory that was developed by Reed in the early 20th century. And what that tells us is that, like, when we have an entire fault, we can no longer assume that the material properties on the fault are uniform. So we have what we call asperities, which are areas where the the crust is stronger, and so it takes longer to um, uh, more shear force to cause them to slip. And this, like, heterogeneity in the fault is what explains both the generations of foreshocks and aftershocks through the asperity and barrier model. So the asperity model, the way that we can think about it is that if we have a fault plane, and we have some strong zones, so these are our asperities, as like the two sides of the fault are like loaded relative to each other, first, like, slippage will occur around our asperities because this is where the strength of the material is less. So for the same amount of displacement, the shear stress will exceed shear strength. So we'll have like aftershocks around the strong areas. And once all these aftershocks are released around our asperities, then it will continue loading these strong zones, and these will be the areas where we'll have our main shock. So this explains these smaller events as the foreshocks before the main earthquake. The barrier model works the same way, but opposite, to explain why we also get aftershocks. So if we have large areas of uniform um, of uniform strength and some areas where we have like higher strength, then if we assume that we start from a uniform stress state, as we are loading the fault, we will have all of this area more or less simultaneously failing, producing the main shock. And then we will have few patches in the rupture plane that still hasn't failed. And so as the fault continues to load, these smaller zones are the ones that will release energy, and this will be the foreshocks. And since in reality we observe both foreshocks and aftershocks, these asperities or these areas of stronger strength is what essentially contributes to both of them. So both models seems to empirically be satisfied, depending on the initial conditions and how the crust is loaded. The asperities also explain why we have ground motion variability. So why we may have like we have stations over the same distance from the fault, like if you have one station here and one station here, the one that is closer to an asperity will have the slippage there will be higher, and so a larger amount of energy will be released. Any question on this? Yes, yes.
Understanding in 3D, like what exactly, this is in 2D, right?
Yes. So in 3D, I'm terrible at drawing, but let me try. The fault, you can assume it's a 2D plane, but like in like those 3D, you have this as the surface. this. And then you have the fault intersecting your surface. So this cross section is a cross section here, right? Is this clear or no? Still is confusing.
So basically, like those arrows that we have made above and below, they are actually behind the plane.
Behind them, yes. So it's like this side moving this way and then this side moving this way. Yes. Yes. Thank you for the clarification. Any other question? Okay. And in general, we'll see that the way that we are estimating how often earthquake happens, the modern way of doing that is by realizing that there needs to be an equilibrium in the energy that we add to the model through the movement of the tectonic plates versus the energy that is released. And this also explains where we expect to have earthquakes versus where the seismicity is lower. This is for example, this shows all the location of the different earthquakes that happen in the past, I think, 20 years in the San Andreas Fault. And what you can see is that over 20 years, there was like a gap around where the Loma Prieta earthquake in 1981 happened. And then because that was the part of the fault that still didn't release the earthquake, that's where it was the most likely location to have a big earthquake. And that was confirmed after the Loma Prieta, where the main shock and the aftershocks from that event filled out that region. Same, and so again, this is what produces like some cycle in the earthquakes. Another example is the Parkfield earthquake, where again, if you have if you count the events versus time, you see the same high magnitude 6 event happening more or less between every 20 and 30 years, because that's how much time it takes for the energy to accumulate again and then released during an earthquake. And in a purely mechanistic way, if we know both the strength of the material and the residual shear stress that is left after the slip occurs, we can predict both when the earthquake is going to happen and the amount of slip, because the amount of slip has to do with the difference in the stress. It has to do with the stress drop, so the difference between the initial and final stress. So if we know both the upper and the lower bound in the stress, the shear stress will be loading, reaching the failure, release until the residual stress, which will be the amount of slip, and then have the cycle repeated over and over again. If we only know the maximum shear strength and we don't know the residual stress, then that means that depending on the current state, we know when the next earthquake is going to happen, but we don't know the amount of slip that earthquake is going to produce. Versus if we know if we can determine the residual stress, then depending on when the earthquake happens, we can estimate what is the amount of slip that it can create. Yes, please.
Slip be like the deformation at the crust.
Yes, the discontinuous deformation on the crust, like on the fault, the plane itself. Yes. Okay, so this has to do with what we will talk about, the constructive interference of seismic events. So before we characterize actually the size of the earthquakes, I think one at least in my way, analogy that can help us to think of like how how small versus big earthquakes will behave is the analogy between a button and a zipper. So you can think of a small earthquake as like a point source where like in a few kilometer zone, you will have the seismic energy released as an individual process. And large earthquakes as a collection of small events that happen along the fault plane. So when you have a large earthquake like a magnitude 7, it's not that the entire fault releases the energy at once, but instead, like each part is releasing energy, loading the next one, and then that causing to overload and release energy itself. So in my mind, it kind of helps to think of like a small earthquake like a button, like something individual, whereas the large earthquake like a zipper, where like you have the rupture propagating along the fault plane and releasing energy. And this is what also causes the large earthquakes to produce stronger ground motion through constructive interference. So if you think of this as the entire fault plane, I'm sorry, actually, if you think the a large earthquake is a collection of small one, you have the earthquake initiated at one point, releasing some energy, then the rupture propagating to the next one, and then that point also releasing energy. So in the direction where the rupture is propagating, in the direction that is parallel to the direction of the propagation, you see the seismic waves are closer together because by the time the first seismic wave traveled, you have the second rupture releasing energy, and so you have this area where the where the seismic waves are interfering with each other, whereas in the direction opposite to the propagation of the rupture, you have the seismic waves spreading apart. And you can see that schematically here, where from the different point sources that are rupturing in the direction away from the rupture, you have long duration ground motions, but small in amplitude. Whereas in the direction where the seismic waves are interfering with each other, you have this constructive interference and then the larger amplitude. And this is again from the Loma Prieta, like from the actual recordings where it started here and it propagated this direction. And so it propagated this direction. So for a station that was opposite to the direction of the propagation, you got a ground motion that had a very long duration. And on a station that was in the direction of the propagation, you had this very large velocity pulse and the constructive interference. So is this helps with your question? Okay. So we talked about small and large earthquakes. So now the next question is, how do we actually characterize the size? And the challenge that we have is we cannot measure the size of the earthquakes itself. We can measure it through the consequences, so through the ground motion. So we want to take the ground shaking that each earthquake is produced, and from that learn something about the source. And there are a number of seismometers that have been used historically from like ancient history and in China, trying to figure out where the earthquake is located and how strong it is, to more modern instruments where they can record the three components of the ground shaking and then use that to determine the level of shaking. The first modern magnitude scale that we have is what we call local or Richter magnitude scale. And that was based on this graph. So what it required is that you had a specific instrument. In that case was a Wood Anderson seismometer. And if you have the recording from that instrument, the distance, the delay between the P and S wave, that would give you the information about how far the earthquake was from where it was recorded, because as you remember in the first lecture, we discussed how P and S waves travel with different speeds. So the delay between them tells us the distance between where it was recorded and the origin of them. So on one axis, we have the distance in seconds, and on the other, we have the maximum amplitude. And so if by identifying the point here and the point and the maximum amplitude and connecting them with a straight line, would give us the local magnitude scale. And this was the first way of a quantifiable way to define the size of the earthquake, because you account for like the attenuation of the seismic waves away from the source. So the same amplitude can be from different earthquakes if those earthquakes from different earthquake sizes if those earthquakes happen at different distances away from where they were recorded. Do you see any issues with this definition of moment magnitude of seismic of earthquake magnitude? Yes, so it requires that you have access to this particular instrument. That's one. Any other? Think about what we saw about the earthquake in California and here in New York. Knowing that the amplitude and the distance, is it enough?
Like the behavior of the rock.
Yes, the attenuation, exactly. Because the magnitude scale is only supposed to define the amount of energy that was released at the source, not how the seismic waves attenuated. So we want to isolate that effect. And so by having this linear relationship applied everywhere, here you would have underestimated the size of the earthquake. Excuse me, you have overestimated the size of the earthquake if you were to apply this in New York, because the seismic waves will not have attenuated as fast as in Southern California. And there is a third reason, what you will see in the literature as magnitude saturation. So this was an analog instrument, and it can only record the ground shaking within the size of the paper, that is where the pencil is moving. So if the shaking is too strong, actually the pen will go away, like go over the span of the paper, and so you will not know what the peak amplitude was. And that's why you will see that this magnitude is good for medium-sized earthquakes, but you cannot record a magnitude 8 or a magnitude 9 size earthquake with this, because it will saturate. And so over the years, different magnitudes were proposed to address this. There is one more challenge if you think about it. Same thing that we talked about, the attenuation. The attenuation changes between regions, so east versus west coast, but it also changes between different seismic waves. So from the previous lecture, we saw how surface waves attenuate a lot slower as compared to body waves. So if you define the peak amplitude as the amplitude of any seismic wave, then you are mixing those two attenuations, because at longer distances you will be recording surface waves. At shorter distances, most likely the peak amplitude will be coming from body waves. And so different types of magnitudes more recently have proposed to address all these challenges that we identified. Surface wave magnitude is one such magnitude scale definition, where again the magnitude of the earthquake is proportional to the log of the amplitude of the seismic waves, but in this case only looking at surface waves, and how far from the epicenter that amplitude was recorded. An equivalent one is body wave magnitude, denoted with small m underscore b, and that looks at the amplitude of body waves, the period of that wave, and again the distance that it has been recorded. Using the duration from the signal can also tell us about the size of the earthquake. And again, if you go to the zipper versus baton analogy, so like releasing energy over a larger magnitude requires like releasing the energy over all these patches, and that creates a ground shaking that is of longer duration as opposed to a small earthquake. So measuring the distance, the duration of the shaking can also be used as a parameter to inform the size of the earthquake. And there is the Japanese meteorological magnitude scale, which looks at the amplitude of, this is for events that have been recorded many kilometers away from the source, and it looks at long period, the amplitude of long period waves. And why long period? That's because it's not only earthquakes that produce shaking in the crust of the earth. You have oceanic waves crashing on the continental shelf and creating vibration. You have wind, you have everything. And most of the noise from these processes is higher frequency seismic waves. So if you look at areas where Earth tends to be quieter, then those seismic waves are attributed to earthquakes. And the most recent and the one that is primarily used now that we have access to seismometers is the seismic moment and moment magnitude. So we define seismic moment as the product of the shear modulus, the area of the rupture, and the average displacement. So, and that's in units of moment. And then that's proportional to the total amount of energy released. So then using this seismic moment and on a log scale defines the moment magnitude. And in modern seismology, this is the scale that is used because it's something that is actually related to the Earth, like there is no influence of path or anything like that. All of these parameters describe the source and the amount of seismic release at the source itself. Yes, please.
How do you do the rupture unit?
Do we have the asperities? Like in the asperity model, the foreshock and like typically you tend to have foreshocks and aftershocks around the main rupture. So you identify the location of those, and the zone that they define is the zone of is the rupture area of the main shock. That's sort of the more traditional and simple way to do it. You can also run like numerical simulations of wave propagation, where you are trying to fit the recordings and the observations, and by parameterizing the source different ways, the source that gives you the best fit of the observation is what you can essentially invert as seismic source. Some other question? And so if some of the some of the coefficients seemed arbitrary between the different scales, like y 7.9 and not 6, and so on, this had to do so that the value that you get from the different magnitudes more or less matches over like medium-sized earthquakes. So between 6 and 7, no matter which scale you use, you will more or less get the same number. But you need to be careful when you use these different scales for either very small or very large earthquakes. And you can also see the saturation that we talked for the local scale and the body wave magnitude, where as the size of the earthquake is increasing, it's either that the local scale cannot record that very large amplitudes, or the amplitudes themselves stop increasing that fast, and that's why you have both the scales flattening out, as opposed to the seismic moment scale, which is continuously increasing. So all of this tells us something about the size of the earthquakes when we have actual observations. But what do if we have only historic, or if we care about historical earthquakes and we try to understand the seismicity of the region for like earthquakes that happen in the 1800s? There are two ways to estimate the magnitude for them. One is through trenching. So we can go where we think the earthquake happens, excavate and find the fault plane, and then there determine both how much it slipped and the extent that rupture cover. And that will give us the information that we need to plug into the seismic moment. Or through the level of damage that we can read in historical records. So there is this modified Mercalli scale, which different numbers in that scale describe different severities in the shaking. So from feeling the earthquake to having widespread damage, and you can relate this to what earthquake, the size of the earthquake that most likely produced that damage. So, like for a modified Mercalli scale of 5 is something between 3.5 and 4, approximately. Now, going back to how we define seismic sources in modern seismology, we talked about the moment. The other parameter that we said is important is the stress drop, and that relates to how compact is, not the total amount of energy, but how compact it is. And for critical ruptures, the equation that can give us the stress drop is this one. So historically, we have observed that the stress drop that we get between different earthquakes is magnitude independent. So this gives us a scale where the amount of displacement is proportional to the square root of the area. And we can use that to understand how the area of the rupture is scaling with different sizes of the earthquake. So if we start, maybe let me create a blank page. So we started by defining that the seismic, oops. We started by defining the seismic moment M as 2/3 of log of seismic moment plus 10.7. Or if you take the constant inside the parentheses is 16.75. So if we substitute the seismic moment as m times area times displacement, and then use the fact that the product inside the log is the sum of the logs, we have 2/3 of log of A plus log of D average plus log of stiffness plus 10.7 is the moment magnitude. And if this is treated as a constant, we have that 2/3 of log of A plus two-thirds of log of D average plus C is equal to the moment magnitude. And we have that from the assumption of constant stress drop that D is proportional to some constant times the square root of the area. So combining these two relationships, we have that 2/3 of log of area plus 1/3 of log of area plus C. And so we can get that the moment magnitude is proportional to log of the rupture area plus a constant. Is this clear? So this can give us directly the relationship between how the rupture area is scaling and the seismic moment and the seismic moment magnitude is scaling. Where would this relationship may fall apart? If we try to draw on this side, so the rupture of the earthquake itself is bounded within the boundaries of the crust, so they cannot exceed. So there will be a point where as the is it showing better? So this is length of the rupture versus width of the rupture, and the product of the two is the area. So as the length of the rupture continues to increase, as the side of the earthquake is increasing, you have the width reaching some plateau value. And this plateau value is the thickness of the crust itself, so it cannot go into the mantle. And so this relationship applies to small to medium-sized earthquakes, but as we go to larger earthquakes that are limited by the width, we need to employ a different assumption, which is either what we call the L model, in which case displacement is increasing proportional to the length, or the W model, where displacement is proportional to the width of the rupture. And so in this case, the displacement after you reach the seismogenic zone thickness will start to increase even faster, because as the area is increasing, only length can increase. Whereas in this model, the displacement will remain constant after you reach the seismogenic zone. And so you can do the same derivation to get how the magnitude should relate with the rupture area for these two assumptions. And this is what we get between like empirical models. The simple model where we assume the log of the area is proportional to the magnitude, and we see that all of these models agree for the small to moderate earthquakes, and then they diverge depending on the assumptions they employ. The last thing maybe to cover today is how the rate of earthquake is changing depending on the size of the earthquake itself. So empirically, we all know that like we can have many magnitude 2s and 3s within a year in a particular region, but the larger earthquakes, because they require more amount of energy to be released or being accumulated so that they can then release it, occur over longer period intervals. And the simplest relationship that is used to describe the number of earthquakes as a function of their magnitude is the Gutenberg-Richter model, which assumes that there is in log space, so the log of the number of earthquakes and magnitude follows a linear relationship. So with a slope that is approximately 1. So for every magnitude, if this is 6, for every magnitude 6, if this is 1, you will have 10 magnitude 5s and 100 magnitude 4s. And this relationship has no bounds, but there is based on what we saw earlier, so the dimensions of the fault itself, there is a maximum magnitude that can happen within its fault. So the update of this model, the truncated exponential model, simply goes and adds an upper limit to the maximum earthquake that can happen within fault. Yes, please. So using this relationship as an example, if you know, like, you know that the San Andreas fault, like, can I try to draw California? Something like that. So if this is the state of California, you have San Andreas fault going offshore, and then inshore, this is about 900 kilometers. And you also know that the thickness in that part of the US is about 15 kilometers deep. So you can have the area as 900 times 15 and plug it in here. So this is the maximum earthquake that this fault can accommodate. And so that gives you the upper limit. That is one way. You can also, like, if you go back, we have a way to define the size of the earthquakes historically. So in regions of the world like Greece, China, India that have been inhabited and we have historical records over thousands of years, people actually go through these records and try to determine what are the different sizes of earthquakes that occurred. And if you know that, like, you haven't recorded any earthquake larger than a magnitude 7, and you expect that if that was feasible, it would have occurred every 100 years, and you have a record of 1,000 years, then you can compute what is the probability of, like, within 1,000-year record of interval not recording something that on average happens every 100 years, and it's increasingly small. So that will also historically tell you what is the larger earthquake that can happen. Yes, please.
Does the rupture duration, can it change for each event? If earthquake happens at the north of the rupture, so
Mm.
it happens for one event, it happens like rupture duration north to south, and can it change for next event south to north?
The Yes, that that has to do with correct. So that's part of what we will call later as part of like the aleatory variability. So the things that are we don't have complete information to determine in advance, and that all has to do with like if you go like if you knew where the asperities and where the seismic gaps are, you could have predicted the direction of the rupture. But if you don't and you simply have a gap, then that can be filled out by an earthquake that's propagating from from here to here or the opposite direction, and that will both satisfy covering like releasing the same amount of seismic energy. Is this answering your question or no? Okay. Any other questions?
I have a question.
Yes, please.
The moment magnitude, you said measures the total energy. Is that the total energy in the earthquake by itself? Is that the total energy released?
Is the total energy released as seismic waves within one earthquake?
So considering in the United States, we don't have very deep faults.
Yes.
So how do we estimate then the area? Maybe length, I think, depth we know because that's how it's up to the mental, but how about the length of the?
Yes. So maybe in a lecture or two, we will spend more time over like seismic hazard analysis and define the different ways that we define the seismic sources. So in areas where we don't know the faults themselves, we use what we call like background seismicity, and it's like you can assume an area where we assume an equal likelihood of an earthquake happening over that entire zone. And the way that you define the size of the earthquake in those zones is only through historical catalogs. So you have the catalog of earthquakes and you are trying to see what is the maximum magnitude that you have recorded and what is the probability for a larger magnitude to occur given the length of the period of the time that you have this catalog over. So the longer it is, the more confident you are that the maximum magnitude that you recorded is closest to the maximum possible magnitude that can be produced. Yeah. Another way to do it is also like this is more it still is a question of open research is what is sort of the largest fault that can exist within a zone and being undetected. So like it goes both ways, right? If you are in an area of low seismicity, that means that typically large faults do not exist because you didn't have that much elastic strain accumulated to produce those faults. So in general, you will also be expecting to have smaller upper maximum limits. Whereas in areas where you have higher seismicity, the faults that produce these large earthquakes are easily identifiable through like changes in the topography and landscape.
What about like areas of water that have large faults? Those are hard to detect now.
Areas of what? Like you mean like subduction zones or like an undersea fault? They are harder to detect. Again, it's maybe this question will best answered when we go through that chapter. Like typically you want to when you build your model, you want to account for the uncertainty that you have. So in those areas, you will have larger bounds. Like we will, again, maybe now it sounds too vague, but there is, to perform a seismic analysis, you need to define the logic tree, and that has all the possible, all the realistic possible models and the weight of how much you trust them. So for an area where you have a subsea fault and you cannot detect it, you will have a large range in that logic tree accounting for like it being only possible to produce small earthquakes or it being possible to produce large earthquakes. And typically what people do is that they run this analysis, they figure out which are the seismic sources that actually contribute to the hazard, because let's say that it's a subsea fault, but it's far from your site, then you don't really care to characterize it. But if it's something that is important for the seismicity at your site location, then you want to invest and like do. They have different methods where like they scan the base of the ocean and they're trying to find trenches and again topographic signs that indicate that there is a fault there and map how long it is. Yeah. Is this enough sufficient at this time or?
Yeah.
Okay. Yeah. Some other question? Okay. Then the last thing I would like to go over today is combining everything together and talking about the equilibrium and how we use this to determine the number of earthquakes that we expect. So we have the loading of the fault, which is equal to the size of is equal to the stiffness times the size of the fault itself, so AF, the slip rate, so the amount of slip between the two plates that is happening within 1 year, times the time t, and then unloading is through the unloading of the fault is happening through the earthquake. So this is simply the summation of the seismic moments for the different magnitudes that can occur. And we can combine this summation into a single relationship because we know that M we know that come on, this is equal to the sum of the seismic moment for its magnitude times, sorry, it's the integral now. From the smallest earthquake, which we typically assume 0, to the maximum earthquake of the seismic moment of that earthquakes times the number of earthquakes that we expect to happen within a year, and N of M, that can come from the Gutenberg-Richter relationship, times dm, times the length of the observation. So the length of the observation is canceling out from both sides because this is the annual rate. And we are left with a relationship where on one side we have the stiffness, the area of the fault, and the slip rate. And on the other side, the seismic moment for each size earthquake, and N of M, which is A plus No, it's it's 10 raised to the power of a plus bm. And that gives you the equation to determine a and b. And if you were to do this, so maybe this is one of the things that I will ask you in a homework, is depending, so this is actually where defining the larger size of the earthquake is actually important, and not only always safe to take the conservative assumption and say that the largest earthquake is as high as possible. Because the amount of loading is constant, if you allow larger earthquakes to happen, that means that in total, less earthquakes will happen because one large earthquake will release more amount of energy, and so there's less budget for the small ones. And so here you see that depending on whether we assume that the maximum magnitude is a 6.5, a 7, or a 7.5, the number of earthquakes that we get is decreasing. So because of all the seismic energy that will be released between 7 and 7.5, you will have less seismic energy, less budget to be released from the small ones, and so you will have less frequent earthquakes. And a lot of the cases, these large earthquakes are so rare that they don't contribute to the hazard, and most of your hazard is coming from the smaller events. So in that case, using a smaller magnitude earthquake will produce higher seismic hazard, which will be uh, uh, more concerning for your structure. I believe that's the last slide that I have. So are there any questions or anything else to discuss?
We go back to the graph that we just talked about. You're saying that you want to kind of estimate something in between because that will cover both cases of larger earthquakes, less frequent, and then smaller earthquakes, more frequent.
Typically, that's the most critical case, but all of that is also location dependent. So what it happens is that you do this analysis, you iterate through this analysis, and you start with the most relaxed assumptions, and you're trying to identify which are the parts of your model that have the highest contribution to the final answer, and then refining those. But this is essentially, I'm showing this here just to create a mental note that it's the kind of naive way of assuming that the largest earthquake is the worst case scenario is not always the case, because that assumes that you will have less earthquakes happening.
And the earthquakes that are most detrimental to structures, that's just dependent on like the region and magnitude.
It depends on this like slope. So for example, if I was to tell you, would you prefer one magnitude 6 or one magnitude 7? Obviously, one magnitude 7 is going to be more devastating. But what if we have 10 magnitude 6s and one magnitude 7? Because one of them randomly can happen to produce a higher ground motion compared to the one magnitude 7. And so in that case, maybe the 10 magnitude 6s are more critical. And all of this has to do with like the slope that you determine from your data, like how many magnitude 6s for one magnitude 7 do you get, how close are the magnitude 6s versus the magnitude 7, and so on.
And those slopes will always be parallel at the start?
Yes, because I can find more plots to show, but in general, you will have like, no, I need to go back to presentation mode. But like you can empirically constrain the slope. And so you will assume, and so you will assume that you know the slope, and what is unknown is this constant alpha. Because, like, again, through historical records, sorry. If you know the magnitude and how many earthquakes you have recorded, you will have, like, for magnitude 6, for magnitude 7, for magnitude 8, or let's say 4, 5, 6, and so on. And you can estimate what is the slope of this model. So it's easy to determine the slope. It's more difficult to understand how high it is and or where you truncate it here. And how do you truncate it here? It's affecting how high this model goes or how it shifts up and down. I think we will see an example and it will make it more clear if it's unclear at this moment. Yeah. Yes, Abba. Yes. The loading is if you have if you know the slip rate, so like if this is the fault between two tectonic plates and you know how the slip rate, so how fast one is moving relative to the other, assuming that your fault is stuck, that's how much energy is accumulating within your fault. So the way that actually you do that is that, like, you have a fault here and you have like a GPS station here, a GPS station here, and if you are to plot on time and displacement, you have one moving like this, the other moving like this. So this is the like deformation that has occurred within this zone that you attribute as being energy released in the fault, locked in the fault. Yes. The you can correct. So the unloading all the energy is all the energy that is released by the earthquakes, and the loading is all the energy that has been accumulating in the fault because of the deformation of the tectonic plates. Yes. Or like maybe does this first slide making sense? So you have like your at rest conditions, and then as this side is moving this way, and this side is moving this way, and you know the slip rate, so that's proportional to the strain that is occurring within a unit of year. That's how much energy, essentially elastic energy, you have locked in the fault. And then when you have an earthquake, then you release that energy. So now if you don't have only one earthquake, but a number of earthquakes of different magnitudes, the total amount of energy that these earthquakes release have to be equal to all the energy that has been accumulated in the fault through the deformation. Is this clear or is it still confusing? Okay.
The energy released from an earthquake, say it has like a lot of energy accumulated, it doesn't have to release that all at once.
No. Yeah, exactly. All of this work on average, so over the span of hundreds or thousands of years.
And it's constantly building.
It's constantly building, and during periods of seismic activity, it's released. Yes. Yes, exactly. Some other question? Okay, then that's it. Thank you so much. And I will see you on Monday then. Or if you have any questions, please stop, either write me an email or stop by my office hours.
Thank you.
Thank you.